Hi everyone, I'm Dr. Sandeep. I'm super excited to welcome you to my new series Signals and Systems Simplified, the concepts every engineer must master. If you have ever wondered what exactly is a signal, why we study systems, or how this subject connects everything in electronics, communication, and control engineering, yes, you are in the right place. This series is designed to take you from confusion to clarity, step by step, concept by concept, so that by the end you don't just remember formulae, you actually understand what is going on beneath them. Let's face it, signals and system can feel abstract. There is math, graphs, transforms, equations everywhere. But the truth is, every modern technology you use, from the smartphone to the radar, ECG machines, or even Spotify audio filters, relies on these very concepts. This series will bridge theory with the real world intuition. I will show you how signals talk to systems, how we can represent them mathematically, and how tools like Fourier and Laplace transforms help engineers understand and manipulate the information more efficiently. Here is what we will cover in a simple structured way. In the first unit, we'll cover what are the signals, what are the systems, and we try to understand the difference between the continuous domain and the discrete domain. Discrete and continuous domains, deterministic and random signals, and why these distinctions really matter for us. Yeah, that's what we see in the first unit. Then we continue on to the second unit, where we look at various operations we perform on the signals, like time shifting, scaling, convolution, all these visualized with animations and intuitive examples, so that more clarity is achieved, and we just get the insight of each of these concepts, which look too mathematical to begin with, but once you get deep inside, dig into it, you understand the very meaning of that, then you start enjoying what they are and why they are and how they will be helpful for our lives. Then we have Fourier series and Fourier transform in the third unit, and see how any complex signal can be represented using just sinusoidals. So this simplifies our life very much, because if we know what happens to a sinusoidal when it goes through a system, then yes, you can talk of any type of signal, because through Fourier series and Fourier transform we can convert any type of signal into a sum of sinusoidals. And if we know what happens with the sinusoidal if it passes through a signal system, then each of these sum of sinusoidals, once they pass through the system, we know what is coming out of that, and one by one we pass through the system and collect them at the receiving side and combine them, get the main signal back, and see how the system transforms the input signal into output signal. Whatever be the type of the signal, it can be any complex signal. Once we know the art of reducing a complex signal into sum of sinusoidals, then if we know what a system does with a sinusoidal, then the work is done. So we can just see what happens with every sinusoidal in that series, and then sum up at the end, and we get what actual output will be from that system for a given signal. So that is the advantage of working with the Fourier series and Fourier transform. That's with the system signal side. Now coming to the system side, we want to know what system is, how it behaves. So to understand the behavior of the system, to analyze the system, what we require is something called Laplace transform. That's what we study in the fourth unit, the Laplace transform, which helps us in analyzing the system. It helps us to understand what poles are, what zeros are, and how these poles and zeros, their positions in the S plane, can help us in getting the stability of the system, what makes a system unstable, and how to get that unstable system back towards stability, and all that. All these can be visually seen through the positions of poles and zeros on the S plane, that is the Laplace plane. So that's what we do at the fourth unit, and in the fifth unit we get into our digital domain. And the digital domain believes in the discrete signals and discrete systems. So the available data, available signals are from the physical world, which are analog in nature, continuous in nature, but we need to convert them into discrete version, and for that we have a process called sampling. So that's what is next unit talks about what sampling is, the different issues related with sampling, how sampling can be done, how efficiently sampling can be done, what are the pros and cons of sampling, and then we try to understand the system in its discrete version. If a system is looked through the lens of a discrete version, how the system looks like, and for that converting a signal into a discrete version or a system into its discrete version, what we require is called a Z or Z transform. So that's what is the foundation for digital signal processing. So we look at the sampling, discrete signals, discrete systems, Z transform, Z transform, all this that are the foundation for digital signal processing in the fifth unit. So here, friends, each episode is short, focused, and packed with real-life connections, practice questions, and intuitive visual explanations. So my goal here is to make learning feel logical, visual, so that we can easily understand, grasp what mathematics is trying to tell us about our signal, about our system, because mathematics is the only way that can tell us without any confusion about any concept. So we need to understand how mathematics is helping us to express the actual meaning of what signal is, what system is, and what happens when a particular signal gets through a system, what comes out, and all that we are going to look at. And here mathematics help us to understand the things easily. So here you just won't hear the equations, you will see them come alive. I will often connect mathematical ideas with the physical meaning, so that when you see a waveform or a spectrum, you will immediately know what it means and why it matters. So by the end of this series, you will not only have a strong grasp on the subject, but also a deeper appreciation of how signals and systems form the language of a modern engineering. So if you are ready to master the core ideas that every engineer must understand, hit that subscribe button, stay tuned, and let's begin this exciting journey together, from signals in time to systems that shape our world. Welcome to Signals and Systems Simplified, where we make complex concepts beautifully simple. Welcome, friends. Thank you.